Okay, good morning, everybody. So today we'll continue our discussion about test for convergence or divergence of series. In particular, we'll look at a couple of examples or some examples for the integral and the comparison tests. And if time allows, then we can go on and move on to some examples for the ratio and the end root test. So, by the way, Fatuma has a question here. Is A equals 1/5 and B equals -1/5? Yeah, I think so. But let me just do a quick check on that. One way you can check your answer is if you carry out the addition. So I guess here you have, what is your denominator for A? I guess you have
It's I think k squared plus 5k.
So you have, hold on. My pencil is not connected to my iPad. Hopefully it's good. There we go. Okay, there you go, finally. So you have 1/5 over k squared plus -1/5 all over, you have k plus, sorry, you just have k here and k plus 5. Is that your setup, Fatuma? You let
Yes.
you factored out k. All right. So one way to check if your answer A and B are correct without going through everything again is you can just add this fraction up again and see if you get 1 over k squared plus 5k. Because if you add these two fractions, you will have 1/5 times k plus 5 minus 1/5 times k all over k times k plus 5, right? So just the usual fraction addition that we do. And then this will give you 1/5 k plus 1 minus 1/5 k over k squared plus 5k. The 1/5 k's will cancel each other out, leaving you with 1 over k squared plus 5k, which is the original fraction that you wanted to decompose. So indeed, your constants A and B are correct, right?
Okay. Thank you.
All right, you're welcome. Why duplicate? Delete, and I'll delete this as well. Come on. All right, so last time, let me just review what we did. We tried the integral test. And then I think we had a couple of examples for the direct comparison test. All right, so just to review these things, let's consider this example. Okay, let me try this one, label it problem 5. Oops. So we have sum from 1 to positive infinity of e to the minus n over n plus cosine squared n, right? So here, what I'll try to do first is to use the direct comparison test, right? So I'll draw up a testing series and say my testing series is the sum of, the numerator is quite simple, so I'll just keep it there. And the denominator, I'll just say it's n from 1 to infinity. And let's see what we get. Do we get a larger or smaller series? Well, here what happened, I ignored cosine squared n, but cosine squared n is a positive number. So when I ignored that positive number, I made the denominator smaller, right? So since the denominator is smaller, the entire fraction is larger, okay? So what we have here is a testing series that is larger than the original series or the given series. So now I am praying that this guy would be convergent so that we have the given series smaller than a convergent series. Because if this turns out to be divergent, then no conclusions can be made because the given series will be smaller than a divergent series. This can either converge or diverge. So the direct comparison test would be inconclusive, right? For this example, again, I want to see if this is convergent or not. I don't think there's an easy way to handle this series at this point. So what I'll do is to take it a little bit, uh, to take it another notch by completely uh, ignoring the denominator. And they agreed that when I ignore the denominator, I am getting a larger series. Agree? Do you agree with this inequality here? If I completely delete the denominator, that means I am not dividing e to the n anymore. Remember, n goes from 1 to infinity, so the denominator is larger than 1. And if I refuse to divide by something larger than 1, I'll get a larger number, right? Because I completely ignore the division. And so now instead of looking at this series, I will look at this series. And how can I see if this is convergent or not? Any guess or any idea? Okay, by now our choices are quite limited because all we have are the integral test and the integral test and direct comparison test. I already did or tried the direct comparison test. So probably here I'll use the integral test. And yeah, Christina, I think, yeah, you're referring to another expansion of this. Yeah, let's put that here just to remind us of what the given series is or what is the testing series we have. Okay, note that I can define f to be e to the minus x, which is also 1 over e to the x. Oops, there's no negative sign in the exponent anymore, right? And you see that for any x greater than or equal to 1, this guy is always greater than 0, right? So that means the first requirement of the integral test is satisfied because we have a function f that is the extension of the terms in the series that is positive, right? The next thing to check is this function f increasing or decreasing? We're hoping that this will decrease so that we can move ahead with the integral test. Now, one way to see if it's increasing or decreasing is to look at the derivative. Okay, the derivative is minus e to the minus x, which is always negative for any x, right? So this means that f is decreasing. Because remember from Cal 1, a negative derivative means that the function f is decreasing. So the function f is positive. It is decreasing. So we can apply the integral test to its corresponding series. So what we do is to compute the improper integral. So here we do the improper integral from 1 to positive infinity of e to the minus n, or e to the minus x dx. We turn it to a limit. As b approaches positive infinity. All right. And then here, I don't want to keep track of the changes in the bounds when I do the u substitution. Actually, yeah, we can do the u substitution in our heads. You can let u to be equal to negative x, giving you du equals negative dx. So this eventually will be e to the negative e to the minus x evaluated from 1 to b. So let me just write that down properly. So this would be the limit of minus e to the minus x evaluated from 1 to b as b approaches positive infinity. Again, all that I did there is to use u substitution to evaluate the integral. Now I can plug in the lower and the upper limits. So we'll have minus e to the minus b plus e to the minus 1. Okay, and what happens when b becomes very, very large? When b becomes very, very large, negative b will go to negative infinity, making the entire first term go to 0. because it would be e to the minus infinity or 1 over e to the infinity. So that means this goes to 0. So the limit is just equal to e to the minus 1. So this means that the improper integral then so does the series e to the minus n going from 1 to positive infinity. So this is convergent. And since our original series, which was e to the minus n over n plus cosine squared n, as n goes from 1 to infinity, is smaller than a convergent series. So by the DCT or the direct comparison test, this guy converges. Oops. Okay. Is that good? Any questions? So this problem is a hybrid between direct comparison test and the integral test. Because again, for the comparison test, I need to come up with a testing series that I know to be convergent or divergent. But actually, even then, the direct comparison test is actually limited in the sense that you can only draw up a conclusion if you get a larger convergent series or a smaller divergent series. Otherwise, no conclusions can be made. Though, at least for me, the direct comparison test is enjoyable because you keep on, it's like solving a puzzle, coming up with a larger or smaller series, but it's very limited in scope because you need to have your testing functions satisfy very stringent conditions, okay? Now, as an alternative to the direct comparison test, you can use the limit comparison test, which will not require you to think of a larger or smaller series, but to compare the series with something that grows with the same magnitude or about a proportional rate. So probably it's better to look at an example. So let's see. So let's do problem 6, which is okay. Okay, so let's test for the convergence of this guy, right? Now, what I'll do is to use limit comparison test. So I'll do limit comparison test with the testing series. So we need to define what our testing series is. Now for the LCT, or if you're planning to use the LCT, you need to look for a series that behaves similarly to the given series. So you can do an asymptotic analysis, meaning ignore terms that becomes insignificant as n becomes very, very large. So for instance, take a look at the numerator. In the numerator, when n is very, very large, minus n is insignificant compared to 3n squared, because 3n squared will grow a lot faster than n for very, very large n's, right? So that means the numerator behaves in a way like 3n squared. All right. Now, how about the denominator? How does it behave? Well, in the long run, the denominator, n to the 4th can be ignored because it will be outgrown by n to the 7th. So thereby implying that the denominator just behaves like the cube root of n to the 7th. Okay, so my plan is to use this as my testing series for the LCT. Now for the LCT, or actually for both comparison tests, I need to know whether my testing series is convergent or not. So I need to determine if this guy will converge. But playing with loss of exponents will allow us to write it as 3n squared over n to the 7/3 Or in a more simpler terms, it could be 3n to the 2 minus 7/3. Remember, loss of exponents when you are dividing two powers of the same base, we simply subtract their exponents. So finally, I can say that the testing series is equal to 3 times n to the negative 1/3. Or in a much nicer form, it's going to be 3 over n to the 1/3. And what can you say about this series that we have? Do we know whether it converges or not? Anybody? Any idea about this? Is it convergent or not? And why say so? Yes, you're correct, Christina. Great. So this is divergent because it is a p-series. So this is divergent. Oops. Because it's a p-series with p equals 1/3, which is less than 1. Remember, p-series will only converge if p is greater than 1. Okay? So we have a divergent series here, and by our analysis, right, we say that this guy will behave around the same way as how 3 to the n to the 1/3 behave, right? But this guy is divergent, so I expect that this will be divergent. Okay? Now to formalize that solution, we'll take the limit of the n terms in our series. So you take the limit of the n term in the given series versus the n term in the testing series. And if that is a constant, then they will both converge or both converge or both diverge. So I'll copy this. I'll put it in the numerator. Actually, it doesn't matter which one you put in the numerator or you put in the denominator, unless you'll have a 1 over 0 or an indeterminate form. But I don't think we'll have a problem with that here. So, okay, I'll evaluate this limit as n approaches infinity. I'm expecting to get a constant here because that's how I designed the testing series, right? So I chose the testing series by doing an asymptotic analysis on how the given series behave. So I'm expecting a constant value here. And I need to really convince you that that's the case. So let's do the calculations here. I'll turn the division into a multiplication. Okay, and then some manipulations more. So I'll have 3 and to the 2 to the 2 plus 1/3. So that's going to be 7/3 minus n to the 4/3 all over 3 cube root of n to the 7th plus n to the 4th. Okay, now you can use the shortcut we learned in Cal 1, because here you can look at the highest power on the top. The highest power in the numerator is n to the 7/3. In the denominator, what's the highest power? Or what's the highest effective power? So in the denominator, you have n to the 7th to be the largest power, but that n to the 7th is trapped inside the cube root. So you can think of it as n to the 7/3 as well. So the denominator has highest power n to the 7/3. The numerator also has higher power n to the 7/3, right? So the technique we learned in Cal 1, we can just divide our leading coefficients. Leading coefficient here is 3. Oops. Leading coefficient in the denominator is 3 as well, because this n to the 7/3 will be multiplied by the 3 outside, so eventually giving us limit equal to 1. And since 1 is a finite number, less than infinity, then both series diverge. Or maybe I can say more explicitly, the given series and going from 2 to positive infinity converges, right? Oh, sorry, not converges, it diverges. Okay. Because the testing series was divergent, right? Because it's a P series with P equals 1/3. And that testing series behaves in a way proportional to the given series. So that means the given series should also diverge. All right. Any questions on that? Okay, have you tried working on homeworks or quizzes? Any questions involving DCT or LCT or the integral test? Or you plan to do that over the weekend? Oh, sure, no worries, Fatuma. Let's shop for a nice example. Let's see. Mm-hmm. Let's try. I'm thinking to try problem 18. But problem 18 is easily seen to be divergent because you can apply the basic divergence test. So if you look at this, if you take the limit of k to the 4th plus 4 over 3k squared plus k cubed as k approaches infinity, right? This is the basic test for divergence. The degree on the numerator is 4. The degree in the denominator is 3. Numerator wins. So that means the limit here is positive infinity, not equal to 0. Thus, this guy is easily seen to be divergent. I thought that would be a good example, but it's not because you can simply use the divergence test for it, or the basic test for divergence for it. Let's see. Let's try problem 10. Let me see if there's a more interesting one than problem 10. Okay, let's try problem 27 instead. Oh, 20? Okay, let's see. Okay, 20. Let's call this problem 7, which is number 20 from the worksheet. All right. So this looks like, this looks like a geometric series, right? But the problem here is that, let's see if we can do a geometric, if we can test it using a geometric series, because it almost looked like a geometric series, except for the plus ones in front of the numerator and in the denominator. So it's not technically a geometric series, but we can compare it with a geometric series and see what we get. So hopefully direct comparison test will work. So what will happen if I drop the if I'll drop the 1 from the denominator? So here what we did is to make the denominator smaller, right? So the denominator is smaller, so the fraction becomes larger. So that means we have this inequality, all right? Now I am praying that this is convergent, because if it is divergent, no conclusions can be made by direct comparison test. But what I can do here before specifying the test is to isolate or to break it down into two fractions. First, I'll have a 1 over 3 to the k plus 2 to the k over 3 to the k. And then you see that this is just 1/3 to the power k plus 2/3 to the power k inside the summation. All right. So the first term is what? The first term is a geometric series, right? With common ratio r equals 1/3 with magnitude less than 1, making it convergent, right? Similarly, the second term is also a geometric series. With common ratio 2/3, which is less than 1. So it's convergent. Therefore, the sum is convergent because it is the sum of two convergent series. That's a lot of things to write. But anyway, ultimately, our conclusion is that this is convergent, all right? Now, the given series is smaller than a convergent series. Again, our layman's interpretation for a convergent series is that this is finite, all right? Now, you have an infinite series that is smaller than a finite series. So that means the given series should also be finite, or in other words, it should be convergent. By the direct comparison test. So I hope by now you realize that the direct comparison test is not really a very fancy test. Actually it's kind of an intuitive or a common sense test, right? So if you have a series that is smaller than a convergent series, it converges. If you have a series that is larger than a divergent series, then it will diverge, which makes sense even if you don't know the proof mathematically, right? Okay, let me see if there's another good example we can work on. Okay, let's see. Okay, let's try this one. Problem 8. Okay, summation of 1 over 5 to the n minus 1 minus 2n. Okay. Now let's try direct comparison test. What if I'll compare it with 1 over 5 to the n? If I compare it with 1 over 5 to the n, I made the denominator larger, right? Because that means I ignored a negative term. So the denominator now is larger. That makes the entire fraction smaller, okay? So this would be smaller, okay? But what can we say about this series? This series is convergent because it is a geometric series with common ratio 1/5, because you can look at 1 over 5 to the n as 1/5 raised to the power n, okay? So if you are using DCT, it would be inconclusive because we see here that the given series is larger than a convergent series. So we know this guy is finite. And what we know is that the given series would be larger than that finite series. Well, this will have still two possibilities. It could be finite with a larger value, or it can be infinite, making it divergent. So DCT is inconclusive in this case, right? What we can do, what we can say is that note that I can do LCT with this. So use LCT with a testing series that has the same asymptotic behavior as the given series, right? So note that so the numerator will behave like 1, or actually behaves like 1. No, behaves exactly as 1. But how about the denominator? What do you think will happen in the denominator in the long run? Again, what we do is to ignore the terms that become insignificant when n becomes very, very large. So what do you think drives the day for the denominator? What's the driving force behind the denominator? Are you just shy to answer the question, or you don't have any idea? I hope you're just shy about it. But anyway, so you just look at what becomes larger, right? When n becomes very, very large, what grows faster? 5 to the n or 2n? Exactly, Christina. 5 to the n grows much faster. Remember our hierarchy of rates of growth? Exponentials will always beat any polynomial, right? So that means the behavior behaves like 5 to the n in the long run. And this would be the testing series that I'm going to use. But what do we know about this? This is a convergent series, right? So because you can write it as this sum, 1 over 5 to the power n, which is convergent because it's a geometric series. With common ratio 1/5, right? Which is less than 1. So the magnitude of the common ratio is less than 1. So since this is convergent and we intuitively have an idea that this guy grows in the same way as the given series, so this guy must be convergent as well. Okay. Now let's prove by the limit comparison test that indeed that given series is convergent. So remember, what we need to do is to find the limit between the ratio of the n terms. So we put on the numerator the n term coming from the given series divided by the n term in the testing series. And we take the limit as n approaches infinity. If this happens to be a constant number, then they will both converge because we already knew that the testing series is convergent, right? So this guy would be, I hope I did the right choice here. Yeah, I think it's easier to do it the other way around. Yeah, hold on. And you will see later why it's easier to do it the other way around. Okay. Now I simplified this as 1 over 5 to the n times 5 to the n minus 2n as n goes to infinity. All right. So as a single fraction, this looks like this. Okay. And then that's why I wanted to reverse the order between the numerator and the denominator, so that here I will have a single term in the denominator. That will make the division term by term possible. So I'll have 1 minus 2n over 5 to the n as n goes to infinity. And again, remember the hierarchy of rates of growth. You have here a linear function versus an exponential function. And remember that exponential functions will always beat a linear function. So in the long run, this goes to 0. Okay. In case you forgot that rate of hierarchy, you can use L'Hopital's rule here, right? because this would be infinity over infinity. But this infinity over infinity, you can use L'Hopital's. So this would be 2 over 5 to the n ln 5 when you take the derivative of top and bottom. So the denominator goes to infinity. So this would be 2 over infinity. So this will become 0, right? But it's very, the hierarchy of rates of growth comes in very handy here, because mentally you can conclude that, oh, okay, denominator grows a lot faster than the numerator, so the limit is 0. So the limit is 1 minus 0, so this would be 1. Christina, I cannot just take a look at the highest exponent. That trick will only work if you have a polynomial on the numerator and a polynomial in the denominator. Unfortunately, in here I have 5 to oops. Here I have 5 to the n, which is not a polynomial. So I cannot do highest exponent or analysis of the degrees because I have exponentials. So yeah. Yeah, not with n. If the exponents are constants, then you're good. You can just compare the exponents. But if it involves the variable, then you cannot do that. All right. Okay, so what we saw here is that this guy and this guy will grow in the almost the same rate, right? Or at least in a proportional rate. So that means they will both converge because this guy turns out to be finite. Okay. So they will both, so the series, the given series, which was 1 over 5 to the n minus 2n, is convergent by the limit comparison test. Again, the reason why it is convergent is that it grows in the same way as how the the convergent geometric series grows. Okay. Again, LCT tells us if you have a finite limit, then the two series will both converge or they will both diverge. In this case, we knew one of the series to be convergent, and so the other series is forced to be convergent as well. Okay. Now I remember there's an interesting problem in the worksheet, so probably I'll show you a solution to that. Unless you have questions for the previous one, just let me know while I'm writing this problem. So this looks a little complicated because here we want to take the summation of 1 over 1 plus 2 plus 3 until k. So, but the thing here is when k becomes large, the nth term becomes close to 0. So that means the basic test for divergence won't apply. Another thing is that this doesn't fall under any, or this seemingly will not fall under any of the special series that we have met earlier. So I guess we need to do a little bit more work for this. But recall, or maybe let's recall this formula that if you're summing up k going from 1 to say capital N, maybe I'll use N instead. N going from 1 to k, then this is k times k plus 1 all over 2. All right, so this is a formula, I guess, that was given in the previous worksheet when you tried to look at the partial sums. So the sum of the first k integers is k times k plus 1 all over 2. So this tells us that the given series is just equal to the sum of 1 over k times k plus 1 all over 2 as k goes from 1 to infinity. Because this guy is exactly this, right? You're summing up n's as n goes from 1 to k. So when you when you simplify this summation as a function of k, you'll get k times k plus 1 all over 2. Okay? And then you can you can write it as 1 over k squared plus k going from 1 to positive infinity. Oh, sorry, there's a 2 there on top. Okay. Now we have two options here. Okay. So first you can solve this as if it's a telescoping series because the denominator can be factored as k times k plus 1. Or another solution would be to try direct comparison tests, right? So actually, you can also try limit comparison test. Maybe I'll do limit comparison test. So note that the given series behave like what? It behaved like the sum from 1 to infinity of 2 over k squared, because the numerator is just 2. So I just copy that over. And then k squared plus k is driven by k squared in the long run, right? Because when k becomes very, very large, k becomes insignificant compared to k squared. So you can simply drop it in the asymptotics, right? So, but what can we say about this guy? Do you remember what type of special series this is? Ideas? Great, that's correct, Christina. It's a p-series. Remember, p-series look like this, 1 over n to the p, where n is the index or the dummy variable. In this case, our dummy variable is k. So the base is k, the dummy variable, then that's good. Then p is the exponent, the constant exponent, and the exponent is 2. So this is a p-series with p equals 2. And is it convergent or not? If you remember, for p-series, we compare p with 1, right? So this is greater than 1, making it convergent. Remember, for p-series are convergent if p is greater than 1, and it is divergent otherwise. Okay. So now we know that the given series behaves in the same way as the convergent p-series, so it must be convergent. But to formalize that idea, we need to take the limit of their k terms. So this would be 2 over k squared plus k all over 2 over k squared. But we already knew what will happen here. This will be a constant, right? Basically here what we're just writing would be the formalism of it. Because that is how we divide how we design the testing series. We built up a testing series that is guaranteed to behave in the same manner as the given series. But that testing series was much easier or much simpler than the given series because it turned out to be a p-series. Okay. So here, just to complete the solution, I can cancel the 2's. So we'll have k squared over k squared plus k as k goes to infinity. And now I can do what Christina suggested earlier, or what she was asking about earlier. The highest exponent on top is 2, highest power in the bottom is 2. So all we need to do is to divide their leading coefficients, which are both to 1. So the limit is equal to 1, which again we expected because that's how we designed the testing series. This is a finite constant, so the given series and the testing series will have the same behavior. In particular, since the given series is convergent, so the given series which is written in a very obscure way earlier, or a very intimidating way earlier, is also convergent. By the limit comparison test. All right. So I don't know if you're still having difficulties with special series or you're just shy to answer my questions. But feel free to tell me if you're having troubles um, with identifying the special series, because you see here, knowing those special series really help, at least from the point of view of the comparison tests, because you need to have an idea of, or you need to have a testing series which you know to converge or not. So you could apply some tests or some fancy tests to really check if they are convergent or not, but it would be a big advantage if you can simply identify them to be a p-series or to be a geometric series, because we can easily know its convergence or divergence without relying on complicated tests. Okay. So any questions? We have 2 minutes left, but I don't think it's enough time to start with the ratio test and the end root test. So maybe what can we do? Okay, maybe to end, let's do problem 29, because it looks like one of those. Uh, yeah, this looks complicated. But Fatuma is asking. Yeah, as always, Fatuma, I will always make a suggestion, whatever topic it is, to practice. You can memorize a different series, but it would be great if you can just make sense of the test so that you don't have to memorize them. Because personally, when I was in my undergrad, I hated this part of the course because I hate memorization, and my approach then was to memorize all the tests, and there are 4, 5, or 6 tests that you need for this chapter. And the thing is that yeah, it's hard to memorize all of them, but with practice, you'll at least get familiar with them, or by doing them repetitively, you will get hang of what's happening, or why does this test make sense. So that will give you a better understanding of those tests, which will free you up from memorizing them. Okay. Now, for instance, I'll do number 29 informally, and hopefully you can do the formal solution. Okay. So this is summation of arctan of k going from 1 to infinity. What do we know about arctan? Well, arctan is just a number between negative pi over 2 to pi over 2. So arctan is just between, negative pi over 2 and pi over 2, or it's just on the interval. So it is a constant, right? So we know that this behaves like summation of a constant all over 1 plus k squared, all right? But what do we know about 1 over 1 plus k squared? 1 over 1 plus k squared behaves like the sum of 1 over k squared. Agree? Because in the long run, this added 1 is insignificant compared to the value of k squared. All right. So, and what is this? What type of series is 1 over k squared? It's a p series, right? It's a p series with k equals 2. With p equals 2. P equals 2 means this is convergent. So this is convergent. This behaves like a convergent series. Oh, this guy turns out to behave like a convergent series as well. So conclusion, this is convergent. And how do you do that? Well, you can use the limit comparison test or the direct comparison test, right? So you can say that, oh, this guy is smaller than pi over 2 over 1 plus k squared, right? Because the maximum value of arctan is pi over 2. But this guy is what? This guy is smaller than pi over 2 over k squared. Actually, this is a totally different solution, but I hope you see the point, okay? Because here I made the denominator smaller, thereby making the fraction larger, and hence that inequality symbol. And this is a convergent p-series, as you have indicated earlier. Given series is smaller than a convergent p-series, that means this is convergent. All right. So just try to answer problems like this, because once you get the hang of it, they are not that difficult. At least if you get if you can analyze them to the tiniest details and then make an intuition out of how this series behaves, then you will have an idea of whether they are converging or not. So that will guide you what test to use. Okay, so practice, practice, and practice. So we'll stop here. On Monday, I'll start talking about some examples of the ratio and the end-root test. I learned that you were already finished with that last Wednesday, so we are a bit behind. But I don't mind doing things slowly. What I want you is to understand the lesson rather than doing everything fast so we can cover everything. So this is the lab after all. So I'll be happy to guide you through in details for these topics, right? So though I don't think ratio and the entry tests are that difficult, so we can definitely answer some problems on that. I already uploaded worksheet 17, which contains some exercises on those two tests. We'll probably try to answer 3 or 4 next time. And if you don't have any much troubles with that, we can proceed with the next section. Okay? I hope that's a good plan. All right, no other questions for now. Hopefully on Monday you'll come up with, or you'll come in the lab with your questions, probably from the homeworks or for the quizzes. I'll be more than happy to guide you on them. All right. Okay, guys. Have a great weekend, and let's see each other again on Monday. Bye, guys.